Thank you very much for the invitation and this very interesting and lively workshop. And I have to start with an apology. I wrote a pretty ambitious abstract, and I will not be able to cover everything that is in the abstract in the 25 minutes or so that have been allocated to me. So I'll try to focus on the local spin current transport in magnetic insulator metal heterostructures. I'd like to start by acknowledging the people who did the work. This was mostly still done in my former group at Walter Meissner Institute in Garching, and Katrin Ganson and Stefan Geprex have been very important people driving these activities. We had a lot of interaction with Helena Gomone, actually affiliated here in Mainz, and Richard Schlitz at my new lab in Dresden also contributed to these results. I'll start by a quick intro to spin Hall magnetoresistance, which A.G. Saito skipped in his overview. So I inserted these slides. That's an effect we discovered together with A.G.'s group and Gerrit Bauer's group a few years back. And the basic idea is to take a magnetic insulator. We love to take yttrium iron garnet, or YIG, and to put a heavy spin Hall active metal on top, and we typically take platinum. And then you drive a charge current in the platinum. That's this thing going into the board here. And by virtue of the spin Hall effect, you generate an orthogonal spin current with a spin accumulation S here at the platinum YIG interface. Now, if that spin accumulation is not collinear with the magnetization in the YIG, with this vector M in pink, then there will be a finite spin transfer torque, and that can be seen as an outflow of spin current from the platinum into the YIG. So there's a dissipation channel for the charge current transporter. In simple terms, you can think of the charge current driving a spin current across the interface into the magnetic insulator. If you reorient the magnetization in the YIG such that it is parallel or antiparallel to the spin accumulation, the spin transfer torque vanishes. And in this case, there is no dissipation. So the resistance of the platinum, although the electrons never really penetrate into the insulator, the resistance of the platinum reflects the orientation of the magnetization, with platinum showing a low resistance for this magnetization configuration and a large resistance if the magnetization is perpendicular to this interface spin accumulation. And that's what we call spin Hall magnetoresistance, and that can formally then be expressed as a resistance which depends on the projection of the magnetization in the YIG onto the spin at the interface, and that gives rise to a cosine square type dependence if you work out the equations. We like to do these spin Hall magnetoresistance experiments not as a function of field magnitude, but as a function of field orientation. So we take a constant magnetic field, say 1 Tesla, and we rotate it along these angles in different planes, in the film plane or perpendicular to the film plane in different configurations. And we see this cosine square modulation of the resistance whenever the magnetization and this spin accumulation can be switched from parallel to perpendicular. So although this might look like a very busy slide, it is quite simple to read. There is two prototypical resistance values, one large resistance here, which occurs whenever the magnetization in the YIG is perpendicular to this interface spin accumulation, and one small resistance value, which arises when the magnetization is parallel to the spin. And if you have a rotation geometry like here, where the magnetization always is perpendicular to that spin accumulation, you only measure the high resistance state. Okay, so this is the basic concept of spin Hall magnetoresistance that we've been happily working with for a few years. But if you think about this more and more, sorry, I don't know what this is, then you realize that there might be some more subtle issues in the game. And that comes from the fact that YIG is a complex, Gary tends to call it a monster, ferrimagnet, which has different iron sites, and these are actually anti-ferromagnetically coupled and result in a net ferrimagnetic moment that people typically treat. So this pink magnetization vector that I was discussing is actually the net moment which can be subdivided into much larger green sublattice magnetizations in this material. And the question we started asking is whether we can see these different sublattice contributions. And we naively drew this picture saying this is the standard spin-Hall magnetoresistance expression. We see this cosine square modulation as a function of a magnetic field orientation. Now we could try to actually express that either in this one or other magnetic sublattice. And you can play these games and realize that actually it is very difficult to disentangle the contributions of different sublattices because they all look the same. And you would have to be very quantitative in disentangling these contributions. If you then get frustrated, eventually you ask for characteristic qualitative changes. And the most dramatic change you can think of is to actually rotate the sublattice magnetization 90 degrees with respect to the external field. If you do that, you add a 90-degree shift in your equations, and that can be seen either as a phase shift or a sign inversion of the magnetoresistance with a large resistance at 0 degrees for conventional spin-Hall magnetoresistance, and then a minimum in the resistance for these 90-degree rotated moments. So we started wondering whether it would be possible to detect canted moments via spin-Hall magnetoresistance. And in principle, this would be possible in YIG. This is a phase diagram, field versus temperature, and you see that there is a large canted phase pocket which is accessible at temperatures below room temperature. Unfortunately, you also need fields of the order of 250 or 300 Tesla to get into that regime, and that is experimentally quite challenging. So we decided to add another level of complexity by inserting another rare earth element, in particular gadolinium, here on the yttrium site, which is non-magnetic typically. And then you get phase diagrams that look like this, which again have a large canted phase pocket, which however now comes down to low magnetic fields and at temperatures close to the so-called compensation temperature when all these different magnetic sublattices cancel out. So we went and tried this idea. This is the spin-Hall magnetoresistance of a YIG platinum bilayer for different temperatures. And you see that there's a temperature dependence in the magnetoresistive effect, but you always find this positive magnetoresistance as indicated by the green arrows. If you then go for gadolinium iron garnet, and for technical issues we added another couple elements in the game here, then you find a positive magnetoresistance at room temperature, which inverts sign at around 80 Kelvin, and then comes back positive at low temperatures. And you can actually trace that out more clearly if you plot the amplitude of the magnetoresistance in YIG platinum as a function of temperature and compare that to this gadolinium iron garnet thing. And you see that there's a clear kink in this magnetoresistance response, which becomes negative around 80 Kelvin. And that can be very nicely understood going back to, first we then went to high fields. So in Munich at the time, we could measure up to something like 7 Tesla, and we color encoded the magnetoresistance that we observed at different magnetic fields. So these green trace that you just saw now is a horizontal line here. So there was this particular thing where you see positive magnetoresistance at high temperature, then this negative dip and positive again. And you can do that for different magnetic fields. And then we went to Grenoble to the high field lab and measured up to 30 Tesla. And you see that this negative phase pocket actually extends to large magnetic fields. And this can be very nicely understood using atomistic spin calculations from Joe Barker, who now calculated the expected spin-Hall magnetoresistance, assuming that iron sublattices dominate the response. And indeed, there seems to be a nice correspondence between what you anticipate from such a canted ferromagnet and what you observe in experiment. So as a take-home message of that first part, we think we indeed can measure these canted magnetic phases, these rotated sublattices in magnetic insulators using spin-Hall magnetoresistance. Now, if you accept that this is true, then you start to be bold. And that was quite a painful boldness the last 2 or 3 years, because we decided to go from these compensating ferrimagnets to true antiferromagnets. And I naively thought this would be a simple endeavor, but it wasn't. So you go back to this sketch, and instead of thinking of canted moments, you now go to something which has a perfectly antiferromagnetic spin structure, meaning 0 net magnetization. And if you again naively think in terms of the net moment, then you should have no spin-Hall magnetoresistance at all because there's no magnetization, right? But if you think in terms of sublattices, then both these two green sublattices contribute the same spin-Hall magnetoresistance signal because they both are parallel or antiparallel to this particular platinum spin accumulation orientation in this configuration. So we again should also be able to measure the spin-Hall magnetoresistance of antiferromagnets if the sublattices or the Néel vector does contribute. The Néel vector is this order parameter in the antiferromagnet, the difference between the sublattice moments, and that would then maybe be the right quantity to describe the spin-Hall magnetoresistance. Now, if you play with antiferromagnets, the unfortunate thing, and that was the hard part, is that all the tricks and games that you learned experimenting with ferromagnets, you have to let go. Because the antiferromagnet essentially is very weakly responding to external magnetic fields, there is only this susceptibility, which is anisotropic. This is a picture I took from Stephen Blundell's textbook. And this anisotropy has to do with the fact that if you apply a magnetic field perpendicular to this uniaxial axis that is encrypted in this spin structure here, then you can actually slightly twist the spins, whereas if you apply the magnetic field along this uniaxial axis, then the antiferromagnet simply does not respond at low temperature. So this would be this finite perpendicular susceptibility in this case and the zero parallel susceptibility at low temperature for this configuration. In cartoon pictures, which I like, you can actually draw the response of this antiferromagnet like this. If you crank up the magnetic field perpendicular to this easy axis, then the spins twist a little bit because they actually gain some Zeeman energy and in exchange lose some exchange energy. Whereas if you do the same game for field along this uniaxial axis, then for quite some fields, the antiferromagnet does not do anything, essentially because the Zeeman energy gain of one spin is exactly balanced by the Zeeman energy loss of the other, unless you reach this spin flop field in which the entire sublattice rotates. So the spins rotate by essentially 90 degrees and then slightly cant towards the field, such that they, again, can gain Zeeman energy. And you can actually simplify that cartoon picture by introducing the so-called exchange approximation, where you now omit all these cantings and just take anti-parallel spin alignments. And then you can draw in the Néel vector as this red thing here. And you see that this spin flop then manifests as a 90-degree rotation of the Néel vector at the spin flop field. So looking at this scheme again, for fields perpendicular to the easy axis, we have essentially no change, and for fields parallel to the easy axis, we have the spin flop transition. You can do that not only for these particular field orientation, but also for intermediate orientations. And the important point to take away from this slide is that if you go to large enough fields, meaning above the spin flop transition, then you find that the Néel vector is orthogonal to the external field in all orientations. So in this regime, we again can manipulate the magnetic order parameter, the Néel vector or the sublattice moments, with an external magnetic field, with the added antiferromagnetic twist, if you wish, that the magnetic sublattices are 90 degrees with respect to the external field. For lower magnetic fields, for very small magnetic fields, the antiferromagnet essentially doesn't do anything. It doesn't care about the external field. And for these intermediate fields, the antiferromagnet slightly reacts, so the Néel order slightly moves away from this uniaxial direction, but it's not really responding nicely. This has all been discussed in a theory paper by AG's group previously, and you see that as a function of field strength, this spin-Hall magnetoresistance response could be quite complex. At large fields, the red curve, you see the cosine square modulation, and then there is these more involved intermediate cases which arise from this complex susceptibility of the antiferromagnet. So we decided to try these type of experiments, and we went for nickel oxide as a simple prototypical uniaxial antiferromagnet with reasonable spin flop fields of the order of a few Tesla. We grew these in thin film form using pulsed laser deposition, and I'll talk about a sample which is 120 nanometers of nickel oxide covered by 3 nanometers of platinum roughly. The magnetoresistance that you observe is beautiful. So you get this very nice cosine square modulation in our angular rotations. Now, in fields at 17 Tesla, it's very pronounced. If you go to 1 Tesla, you still can see these effects. And if you zoom in, you get these type of results. So we seem to have a continuous increase of the magnetoresistance and not at all this sudden onset of a clear response above the spin flop field. So if you plot the amplitude of the effect, you see this continuous increase within the apparent saturation at high fields. And this is something that really puzzled us for quite a while, and that's where Helena Gönnenwein came in and pointed out that actually the antiferromagnets not only are nickel oxide not only is magnetically interesting, but there's also very strong magnetostrictive effects. So in these systems, you will have different domains forming, and these domains, because of strain, actually behave in a very complex way. So if you start with antiferromagnetic domains like this and apply external fields, then gradually these domains will be removed until you reach this fully polarized state, which looks like a spin-flopped configuration. And the magnetoelastic, the stress in the sample, actually acts as a counterforce, a counterbalance, which prevents this domain reconfiguration happening at low magnetic fields. Likewise, if you apply a magnetic field in another direction in this triaxial easy plane, then you have continuous domain growth until you reach this saturated state. So that very intuitively, these type of pictures intuitively explain why the spin-Hall magnetoresistance continuously increases, essentially because you more and more reach this one homogeneous magnetization state. And you can take the simulations that Helena put forward using these de-stressing fields and put them on top of our data. We should see a pronounced kink here when actually we reach this de-stressing fields, which does not seem to be so clear in our data, but other than that, the agreement is very good. And actually, we can use the same type of simulation also for single crystal experiments from Van Wees's group, where they see very similar trends with slightly different field scales because the single crystals seem to have different spin flop and strain fields. That already brings me to my summary. I hope I could give you a flavor that this spin current induced magnetoresistance across interfaces between metals and insulators is useful to actually look at sublattice magnetizations and then antiferromagnets. But since chromium dioxide popped out in the discussion, let me quickly show 2 slides on this material as well. So we played, as you might have heard from my comment, we played quite a bit also with CR203 in collaboration with Tobias Kossup and Denis Makarov from Rossendorf. And we tried to do magnetoresistance experiments, spin-Hall magnetoresistance experiments in this material. And it turns out that in at least all the samples that we could put our hands on, we never saw spin flop. However, we saw a beautiful spin-Hall magnetoresistance type response if we would heat the chromium dioxide above the nail temperature. So there seems to be a strong spin-Hall magnetoresistance-like response when the chromium 203 is not antiferromagnetically ordered on the long range anymore.
The sign is ferromagnetic-like?
Yes. Yes, so this looks like a paramagnetic spin-Hall magnetoresistance, which we don't understand at all.
Could it just be paramagnetic?
Well, then it would need to have a very high spin polarization. Yes, so it could be sort of, remaining correlations from the antiferromagnetism above the nail temperature, such that you have sort of small local spin arrangements which then behave paramagnetically. But we have no robust theoretical model or sort of the evidence that this happens.
It's linear in magnetic field?
Well, we tried to measure the field dependence. It seems to saturate. That's, you tell me what the typical paramagnetic response of that system should be. I would expect that is pretty Brillouin-like. That seems not to fit, but our data sets are not good enough to really draw robust conclusions in this direction.
One can look directly at susceptibility, right? Like a complement.
Yes, but this is thin film, so susceptibility is really, really difficult because you have a substrate beneath which essentially blurs everything that you'd like to extract. So.
Do these things frustrate system? I'm not sure about this.
I don't think so. I think, well, at least the people making these samples, Tobias and Dennis, they claim that they have beautiful single phase Cr2O3, and that seems to be true. So the samples are really high quality, and it should be a nice uniaxial antiferromagnet with a well-defined uniaxial, not triaxial, but uniaxial axis. But we don't see any spin-hole magnetic resistance. Yes, it can be more complex, but we don't know about these samples and we don't know about the interface. And again, it's very difficult to magnetically probe these systems since they're antiferromagnetic and the typical tricks you can play don't work.
Because when we make a cobalt chromium, it's highly spin frustrated. And above the temperature, even the room temperature, you can observe as a mark. So we related it to high ferromagnetic acceptability.
But then, yeah, so maybe something is operational here as well. Okay, well, okay, we're discussing anyway. Yeah.
So wondering if you can do the same thing on a hematite, iron 203.
We tried. Or we are trying, let's put it that way. So the thin films so far did not seem to work. It seems to be a materials issue that my take, but that's sort of very experimental, statistical gut feeling.
Wait for 2 more talks.
Okay, so maybe Matthias has something. We're now working on single crystals, which show Morin transitions. So nice hematite, but it's...
If you go back to that slide with the gadolinium and garnet high field data and the simulations, I thought there was something quickly just so the simulation shows at 300K.
320, yes, and we see at 80. That's a little, this dirty experimental trick. We thought it would be smart not to use gadolinium iron garnet because the pure compound has a compensating temperature of about 320 Kelvin. So that's why Joe, in his calculations, he uses simple gadolinium iron garnets, the clean phase, and he finds the right compensation temperature. Whereas in our samples, we introduced gadolinium and indium and yttrium, because that is known in the literature that you can actually shift down the compensation temperature below room temperature. And we thought that would be a smart move because that would allow us experimentally to access this transition temperature very easily. On hindsight, after doing many experiments with these samples, that might not have been so smart, because then comparing to calculations always is with this caveat that we look at a material which has a different transition temperature or compensation temperature than the pure compound would have. But other than that, so if you just renormalize the temperature, the behavior should be very similar.
I speaking fully get the last point of this nickel oxide. So what is main outcome? You expect it to be flop, but because of magnetic friction, you never seen it, or?
Yes. So essentially, this spin flop picture would be valid if you were able to prepare these samples in a single domain state and then apply continuously increase the field strength along, so prepare a single domain state along one of these easy axes and then apply magnetic field. But that typically never happens because these elastic effects result in multi-domain configurations. So it's very difficult to get these samples single domain, if you wish. So that's what's sort of the added issue in the game.
So this multi-domain structure, is it like random or somehow there are 3 domains like you draw in?
No, this is just a representation that shall illustrate that actually at zero field, at small magnetic fields, we think there should be roughly the same amount, the same total fraction of these different domains, but they're very sort of randomly distributed. And this is just for drawing purposes to illustrate the ratio of these different domains. Yes.